Hi guys. So we have our last unit here. Yeah, there we go. Okay. Unit 9. Fun unit. I love this unit. So what we have going on here is we're going to talk about that quantum phenomena weirdness and we get to discuss dual nature of particles, right? Do we have this wave? Are we a particle? Do we have evidence that suggests that? What's going on with the Bohr model and electrons at fixed energy levels, and then the radioactive decay, like nuclear stuff. So we're going to look at that and half-life, all that good things. Relativity, special and general relativity. So that's what we're covering in this unit. First idea. First idea is this concept of an electromagnetic wave. That we can have a wave that's composed of both, a component of electrical field, a component of magnetic field, and it can propagate or propagate itself through space. It doesn't have to have a medium in which to travel, okay? And we're able to then, through experimentation, observation, determine that this is not just visible light, but it's an entire spectrum, and the gamma and X-rays as well as radio waves that we've seen all are electromagnetic waves. The difference between them is their wavelength, and since they're all traveling at the same speed, they have different frequencies too, right? Do you remember our equation that the velocity of a wave is the wavelength multiplied by the frequency? And so if this remains the same, and one of these is changing, then the other must change as well. And this is an example of inversely proportional, that when a wavelength gets big, the frequency gets small. When the frequency gets big, the wavelength gets small. Okay? All right. So we have this electromagnetic radiation, okay? And it turns out that electrons can absorb this radiation and they can start vibrating with a similar frequency. And consider this for a moment, because light has a frequency of in the realm of times 10 to the 14th hertz, okay? Think of how many zeros that is. Think of how many waves per second or vibrations per second that is. And we as massive objects are not capable of vibrating at that kind of frequency. We have too much inertia, right? So we take something with a really small mass and it's easy to change that motion, right? And so we can more easily vibrate and move at a higher frequency. It turns out electrons can vibrate at a similar frequency. Now let's talk about what opaque is, and let's talk about, let's see, I have it here. When something's opaque, then an electromagnetic wave is not passing through it, it is being absorbed, okay? And so we are able to see through glass because the range of electromagnetic waves that visible light contains is capable of passing through that glass. And so it's transparent for visible light, but is not transparent. You could define it as opaque in regards to ultraviolet or infrared. And it takes it in and it absorbs it. That's why glass can start to feel warm, because it's taking in that ultraviolet electromagnetic radiation. But we can see through it because the EM, electromagnetic radiation of visible light, is capable of passing through the glass. Same kind of thing with our atmosphere. Visible light passes through the atmosphere, and we also get some ultraviolet, infrared, all that. But there's quite a bit of this radiation that's not making it through our atmosphere, and different gases can block those different components so that our protection's pretty good, and then there's some places that we still get that EM traveling through. Couple of definitions that I want you to be aware of. The first one is umbra and then penumbra. So have you ever noticed or seen when a shadow is really defined and clear? It is a total shadow. That's called an umbra. And then when we have a softer shadow, or maybe a shadow that's like in ripples, things like that, it's an incomplete shadow, and that's called a penumbra. Here's another interesting thing about light. We can use a polarized filter to polarize or orient light. So light sources tend to emit light in all orientations, right? X, Y, Z, etc. But if we force that light to pass through little slits of transparent and opaque, and they can only go through the transparent components, then the only ones that make it through are the ones that are oriented the same way as that polarized light. Okay? And what's cool about this is we've viewed and used this phenomenon in multiple ways. Let me show you. This is a polarized filter, okay? And so there are tiny little portions of, strips of this filter that light can pass through. And so we can polarize the light all in one direction. And then we can polarize the light in another direction, okay? So if light going through this filter is being polarized one way, and we cut off the polarized light with another polarized sheet, see, they're the same, so that light is able to pass through. But as soon as we cut off both, then there's no path that the light can travel through, that we've blocked the light completely, because if we're going to force that light to polarize one direction and then we put a second polarized sheet that will not allow that direction of polarized light to pass through, then it won't. So yeah, filters, polarized filters, really interesting. We've seen this occur when light reflects off of certain surfaces, non-metallic, such as like glass, water, roads, okay? And if we have these horizontal surfaces, what tends to happen is this light, this unpolarized light with all different types of orientation, after they reflect, they tend to become polarized. They tend to orient all the same direction, congruent with the surface that it was reflecting off of. So we have this horizontal polarized light. And so you may have seen, these expensive polarized sunglasses. And if we are reflecting off of water and roads, that's where we get that glare, that reflected light. And if we have a polarized sunglass that cuts off the horizontal light, then we will no longer see those glares that are all polarized horizontal due to the reflection. And so then we only see the vertical. But that's all encompassing, right? We get vertical components of light from everywhere else, so we're able to see all of that. What we don't see is those glares or reflections. And this is that same process with, they have those glasses that makes it easier to see fish when you're fishing. Same idea. That when the light reflects off of the water, it's polarized, right? It's oriented all one direction. And so then if we have glasses that cut that off, then we no longer see the glare of that light off of the water. Okay. that's polarized light. Now let's talk about, that was mostly the wave component. Let's talk about the particle component of light. Where are we at time-wise? Okay. So we have lots of different experimentation and that showed us that light is a wave. The double slit experiment, more than anything, was a great example of that. And in the slides, there's a video that describes what's happening with the double slit experiment. So if you haven't watched that, go back and watch that video. Okay? And so we have this dual nature. Is light a wave? Is it a particle? And then the video talks about, are electrons waves? Are they particles? And this idea was developed by Planck, and this physicist, and saying that what if energy at a quantum level is not continuous? Let me give you an example of this. I'm going to draw this actually up. This will be easier. Let's say that if I'm viewing energy on the macro level, like kinetic or potential, and I can increase continually in that energy as time passes. Okay. Now, what Planck is saying is, if I zoom in on this, and that I'm not viewing energy as a macro concept, that at a quantum level, it is not continuous. Like if I zoom in on this little part, it's not a continuous line. What is actually happening? Okay, again, we're going to just zoom in on a tiny little part of this. Okay, so that's what this will be. We'll be zooming in. That the energy is actually little chunks. And then when we see this all at once, it looks like a continuous line, right? That we are smoothly transitioning from lower energy to higher energy. But at a quantum level, we have a certain amount of energy, and then we're capable of jumping to the next energy level, but there's no in between. We don't transition from one to the other. We instantly go from one to the other, okay? And electrons do this. We see that we can jump from one energy level to another one, but that electrons don't exist in between those energy levels. Okay, so if energy can be chunked, and he gave a name for this of a quantum, then we can describe that chunk as a particle, and Einstein gave the name to this chunk of light a photon. Okay, so a photon is a massless particle of light. Yes, massless particle. It's quite the concept, isn't it? So if we have this particle, then what evidence of that could we see? Okay, so that's what our next video is going to be about, is we're going to talk about the photoelectric effect and atomic emission spectra. Oh, and I'll show you an image of our wave-particle duality as well. Okay? All right. Wonderful. On to the next video.